Hey everyone, welcome to The Explainer. Today we're unpacking a fascinating, but honestly pretty urgent topic that tends to get completely overshadowed by the bright, sunny promise of renewable energy. Look, we all love the idea of a green future powered by solar panels, right? But what actually happens when those panels reach the end of their lifespan? Well, today, we're systematically breaking down the hidden end-of-life challenges of solar technology. We're going to look at the science, the massive impending wave of waste, and the harsh economic realities of recycling these solar cells.
Okay, let's dive right into our roadmap for today. We'll be covering the looming solar waste crisis, what makes panels toxic, how to recycle solar cells, silicon versus thin film tech, and finally, the high cost of recycling.
Starting with Section 1, the looming solar waste crisis. It's a bit of a clean energy paradox, really. Now, solar panels are absolutely incredible tools, and it's primarily because of this staggering number right here, 173,000 terawatts. That is the amount of continuous solar energy striking our planet at any given moment. To put that into perspective, that's literally 10,000 times the entire world's total energy use. So it completely validates why governments everywhere are pushing so hard for a transition to solar power. But this rapid transition, it comes with a delayed catch. The average lifespan of a typical solar panel is only about 25 years. That means all those panels installed during the early 2000s solar boom, yeah, they are rapidly approaching retirement. Now, what's really interesting, and honestly kind of terrifying about this early retirement wave, is the sheer scale of the problem. Worldwide solar cell waste is estimated to reach up to 78 billion kilograms by the year 2050. 78 billion kilograms. We are talking about an absolute mountain of retired modules. And as we're about to see, managing this specific type of waste is definitely not as simple as just tossing it into your local blue recycling bin.
Which brings us to a frankly shocking statistic. Currently, only about 10% of photovoltaic or PV modules are actually recycled globally. Just 10%. You might be wondering, why so incredibly low? Well, a massive factor is the lack of concrete regulations mandating their disposal. The infrastructure is just severely lagging behind the deployment. In fact, right now there's only one dedicated PV recycling plant in all of Europe, and believe it or not, the situation is even worse on other continents.
Moving to Section 2, what makes panels toxic? The hidden dangers inside. So, a common question is, why can't we just leave these old panels in a regular landfill? Well, it's because when solar cells break down or degrade, they release an alarming cocktail of toxic elements. We are talking about lead, cadmium, chromium, arsenic, the whole shebang. And what's absolutely crucial to understand here is that the fastest growing market, which is thin film PV technology, actually contains considerably more of these toxic materials than your traditional silicon panels. If these modules are just dumped, this highly toxic cocktail leaches straight into our soil and our groundwater. Not good.
So, on to Section 3, how to recycle solar cells, the deconstruction process.
We obviously can't just give up on solar technology, right? So how do we actually handle this safely? Let's move to the solution and see how this builds. Safely dismantling a solar PV panel is a high-stakes, three-step teardown process. The industry generally relies on physical treatment, followed by thermal treatment, and then finally, chemical treatment. And each of these stages targets a very specific layer of the solar cell architecture.
Step 1 is the physical treatment. Basically, the panel has to be dismantled part by part. First, the recyclers remove the junction box and the embedded cables. But the absolute most critical step here is removing the surrounding aluminum frame. That frame is paramount. It's the very last component attached during manufacturing, and it completely seals the module edges from the environment while giving the panel its mechanical strength. Once you get those parts off, the remaining panel is shredded and then tested to figure out its toxicity levels for disposal.
Step 2 is thermal treatment. This is where we bring the heat. Recyclers combust the shredded waste at extremely high temperatures. We're talking around 600 degrees Celsius, which, for context, is significantly hotter than a commercial pizza oven. The whole goal here is to burn away the binding layers so you can separate the valuable silicone. But there's a massive catch. Burning these materials releases hazardous gas. You literally have to actively capture and trap the vaporized metals during this process, otherwise you're just creating a secondary environmental disaster.
Finally, step 3 is chemical treatment. This usually happens right after the thermal stage. The separated materials are fed into a chemical process to further purify and extract the most valuable elements. But, just like with the thermal stage, it carries a huge risk of hazardous gas emissions.
Controlling these toxic gases across both of these stages isn't just difficult, it is for sure one of the single biggest scientific bottlenecks in the entire recycling procedure.
Section 4. Silicon versus thin film tech. The trade-offs in recycling technologies.
Because not all solar panels are created equal, the recycling methods have to adapt. And this brilliantly illustrates the headache recyclers face. With standard silicon cells, every current solution has a significant drawback. Physical disintegration? Sure, it's efficient, but it damages the cells and causes emissions. Thermal treatment perfectly isolates the cell and removes those binding agents, but man, it is incredibly expensive. And mechanical processes are simple and offer high-purity recovery, but they completely fail to remove dissolved solids. It's just a constant game of trade-offs.
Now, contrast that with thin film recycling, which relies really heavily on intense material purification. You've got hydrometallurgical processes, which essentially use liquids. These are great because they easily fit into existing industrial setups, but the downside is you end up losing a lot of valuable materials in the slag. Then you have pyrometallurgical processes, which use extreme heat. These suffer from incredibly long separation times and highly complex chemistry. It is a notoriously difficult scientific puzzle to try and solve at an industrial scale.
Which brings us to our final section, number 5, the high cost of recycling, the economic barrier.
Okay, so if we actually have the scientific solutions to manage these toxic materials, why is only 10% of global PV waste being recycled? To understand this green dilemma, we really have to look at something called eco-efficiency. This concept evaluates a product's total life cycle, so the energy consumed to make it, its overall environmental impact, and the cost of the recycling process itself. Then it compares all of that against the actual market value of the recovered materials. For recycling to actually happen in the real world, the eco-efficiency must be high enough to make financial sense.
So the crucial point is this brutal economic reality. Right now, proper recycling is just too pricey. It requires huge amounts of energy, super expensive tech, and often it yields pretty poor quality output for metals like aluminum and copper. Compare that to the landfill option. Currently, simply tossing these panels into a hole in the ground is significantly cheaper. Because of sheer economics, dumping is actually more attractive to many decision makers today, even though it literally leaves toxic remains sitting in our earth.
Look, the rate of increasing end-of-life solar panels is vastly outpacing our progress in building the recycling infrastructure to handle them. If we want a truly green future, we absolutely cannot ignore the end of the line. So I'm going to leave you with this to ponder. Can our social and political organizations mobilize to establish an effective, economically viable recycling infrastructure before that 78 billion kilograms of toxic waste buries us by 2050? The clock is ticking on our clean energy solutions. Thanks for joining me on this explainer, and keep questioning the full life cycle of the technology around you.